to think about this example in the book. It's one of the stereotypical charge distributions. I just found everything in the demo room this morning, so I could just put it together. So you have charges on a ring, uniform distribution of charges on a ring. Should be closer to the microphone. Uniform distribution of charges here, and we're looking at trying to calculate the electric field at some point here. Okay, so there's two segments of the charge that we're going to consider. It's the charge that is located in this segment over here, and the charge that is located in this segment over here. We want to pair them that way because, as we have already seen in a couple of examples, the electric field at this location, due to the charges here, say points that way, and the electric field at this same location due to the charges right opposite to this, right? And because those distances, this distance and that distance, and the amount of charge is the same, these vectors are the same, and this component and that component of the electric field would cancel each other. So the resulting electric field of these two charges is an electric field that points straight along this axis, right? Now those are not the only two charges in the ring, of course, but the contribution from the charges that are a little off, right? You can pair them again this way, and you see that again those two charges will produce an electric field that points straight along the axis of this ring. So all of the charges along the ring, you can pair them that way, and the contribution from all of those charges to the electric field at this point is to have a field pointing this way. So you already know that the electric field at this point along the axis of a ring should point along the axis. That you know for sure, right? You might think that this problem is going to involve some integration, just like it did before for the line of charge. We had to integrate, although we didn't do it here, but that's how you arrive to the result we're discussing. You might think that here you have to integrate also, but turns out you don't, because the integration would show up whenever you're trying to calculate the contribution from different charges on the object, but only if those charges are at different distances from the point where you're calculating it, right? In this case, the point P in your calculation, every section of every element of charge on this ring is at the same distance from point P. So the contribution, all of the electric field, real electric field E that point in this direction, they all have the same magnitude, and they point in the same direction. So that's just a summation, a very simple summation, and does not involve integrating anything. So all that you have to do is consider the contribution of those pairs of charges. So you consider the contribution of the charge here and the charge here, and as we just saw there, the electric field of one goes this way, the electric field of the other one goes this way. There is an angle theta there defined by the size of the ring and the distance from the center of the ring. So if you're a distance r, let's say, actually the book calls it z, so I'm going to be more careful with that. So let's say that this is the z axis, and you're a distance z from the center. And the ring, of course, has a radius, and you can call that r, right? So this angle theta is what determines the components. So the net electric field there is going to be the sum of the charges, of the electric fields produced by the charges along the ring. Each one of those charges contributes with an electric field, E sub I, and we're going to have to compute the cosine of that, because we know that the vertical component cancels by pairs, so that will be cosine of theta. Okay. The little electric field magnitudes are as much charge as you have in that section of the ring divided by the distance, which is square, which is r squared plus z squared. Right? So you're going to plug that in here, multiply by the cosine. The cosine of theta is going to be z divided by square root of r squared plus z squared. And so when you put all that together,
you get that the total electric field, which you already know that it's going to go in the z axis, it's going to be the sum of the electric field produced by all of the pieces. Let's say that you have n pieces. You add all of the electric fields along the z direction, because in the y direction they will cancel. The magnitude of the electric field produced by the charge I, it would be k times the amount of charge delta q divided by the distance between the charge and the point P, which is r squared plus z squared. This multiplied by the cosine of theta. Theta, the cosine of theta is the adjacent z divided by r squared plus z squared. Now notice that every term in the summation is constant, because every piece of the charge in the ring is at the same distance r from the point P. So because that's a constant, we can pull it out of the summation. Everything that is doesn't change. So inside the summation we get delta Qi, and we're summing over all of the pieces in which we divided the charge of the ring. So if we add the charge of all of the different pieces in which we divided the charge of the ring, we obviously get the total charge on the ring. So the sum of all the delta Q's is equal to the total charge Q on the ring. So the final answer for the electric field, which we know goes in the z direction, is, and it depends on the distance to the ring, we're calling z that distance, is k, this total sum of the charges is q, z divided by r squared plus z squared to the 3/2. So this is the electric field produced by the ring along the axis that goes through the middle of the ring. Now let's consider what would happen if we put a charge in the middle of a ring. This is like one of the homework problems that you have assigned for this week. So we're trying to figure out what's the force on a negative charge located at distance d from the center of the ring. So what is the motion of this charge? The ring is positively charged, so it has an electric field along the z-axis that points to the right. On the other side of the ring, it will produce an electric field pointing to the left. So the force acting on the negatively charged particle would be to the left when the particle is to the right of the ring, and it would be to the right when the particle is to the left side of the ring. This is because remember that the force is the charge times the electric field. If the charge is negative, then the direction of the force is going to be opposite to the direction of the electric field. This is what you have when the charge is negative. So this tells you that the force acting on a negatively charged particle near the center of the ring is going to be a restoring force. If you pull the charge to the right, the force tries to bring it back to the center, a force points to the left. If the particle goes to the left of the center, then the force tries to push it back towards the center, to the right. So this is the characteristic of a restoring force. This is the same kind of force that acts on a particle attached to a spring, a restoring force that makes the particle oscillate about the equilibrium point. So let's see how much is that force. If we know that the electric field at location z is the expression we calculated before, the force is given by simply multiplying this by the charge of the particle. Now let's approximate and say that where the particle is going to move not too far away from the center of the ring. So we say that d is much smaller than a, the radius of the ring. Now the force, as a function of the distance d, we can approximate it by finding an approximate expression for the electric field and multiplying it by minus q0. This approximate expression is for the electric field is k q divided by a to the third power times d. You can get this expression from the equation that we derived before. So in this expression, you see that we have a constant term that we have circled there, multiplying d, the distance, the displacement from the center. This should remind you of the behavior of the force of a spring. When a mass is attached to a spring, the force that the spring puts on the mass is minus k times the displacement, delta x. So for a mass attached to a spring, we know that the solution to this problem is an oscillatory motion that has an angular frequency, omega, which is given by the square root of k divided by m. So for the problem at hand with the ring and the charge, the constant that is going to play the role of the spring constant is what's inside the circle, k q0q divided by a to the third power. This is going to be our effective constant, and the motion is going to be oscillatory with an angular frequency given by the square root of our effective constant, spring constant, let's write it k effective, divided by the mass of the charged particle. So this is how you would solve the problem in the homework dealing with the oscillatory motion of a particle placed near the center of the ring.